Classically, entropy is the measure of a system's thermal energy unavailable for conversion into mechanical work. Statistical entropy is the application of probability theory to the thermodynamic principle of entropy. It shows that entropy is a measure of the amount of disorder in a system. The number of equivalent microstates, or the number of possible ways for a given condition to occur, is denoted as omega. In this formula, entropy is denoted as S. K is the Boltzmann constant. This results in the formula of S equals K times the natural logarithm of omega. This shows that entropy is a measure of the disorder of a system. As a result, the larger a system's entropy, the more disordered it is. And the smaller a system's entropy, the more ordered it is. The second law of thermodynamics indicates that entropy tends to increase. Because entropy is related to disorder, the second law also indicates that a system's degree of disorder tends to increase. The only way to decrease a system's entropy, that is, increase its order, is for work to be performed on the system. The problem is that while the second law shows that energy applied to a system can reduce its entropy, it does not show how the manner in which energy is applied to a system affects its entropy. It does not show the difference between construction work and a bomb. Construction work reduces a system's entropy. However, the explosion of a bomb increases a system's entropy. Unfortunately, the second law of thermodynamics does not show the difference. So an additional principle is needed to show this difference. This additional principle relates the degree of order or disorder with which energy is applied to a system to the degree of order or disorder that it produces in that system. If energy is applied to a system in a manner more ordered than that system's degree of order, then it increases the system's order. If, on the other hand, energy is applied to a system in a manner more disordered than that system's degree of disorder, then it increases the system's disorder. To show the mathematical relationship with entropy, let's define the following. The number of equivalent microstates of the applied energy is omega sub E. The number of initial equivalent microstates of the system is omega sub S. The change in entropy is denoted as delta S. K is the Boltzmann constant. This results in delta S max equaling K times the natural logarithm of omega E over omega S. This shows the general direction that applying energy to a system will move the entropy of that system. The actual change in entropy results from the amount of energy actually applied to the system. This principle can be reduced to two statements. The general application of energy to a system in a manner more random than the system will increase the entropy of that system. And the general application of energy to a system in a manner less random than that system will decrease the entropy of that system. As an example of this principle, it shows the difference between construction work and a bomb. In that, construction work is less random than the degree of randomness of the raw material, so it decreases its entropy. And a bomb explosion is more random than the degree of randomness of the raw material, so it increases its entropy. Consider what happens when a system is cooled. At the molecular level, heat energy is applied in a manner more random than the system, so as a result, heat increases entropy. As a system cools, the molecular forces between molecules applies energy in a manner less random than the system, and so cooling decreases entropy. The goal of straightening up a room is to reduce the room's entropy. If you just toss things around in a more random manner than they already are, you will actually increase the room's entropy. However, if you place things around a room in a more ordered manner than they already are, you will decrease the room's entropy. This principle applies to all systems, since it is both system and path independent. The basic principle is that adding more randomness to a system makes it more random, and adding more order to a system makes it more organized. It shows that to get a given degree of order, one needs to apply energy with at least the same degree of order. That means to get a given degree of order in a system, you need at least that same degree of order outside the system. Living systems are generally conservative systems, in that the increase of their entropy over time is slower than that of non-living systems. The reason living systems are generally conservative is that they apply energy to maintain themselves against degeneration. However, they still increase their entropy because no matter how organized their application of energy is, it is still always a little more disordered than the living system itself. As such, living systems increase their entropy over time, but more slowly than a non-living system. In conclusion, applying energy to a system in a manner more random than the system increases the system's randomness. On the other hand, applying energy to a system in a manner more ordered than the system increases the order of that system. The result is that to raise a system to a given degree of order requires applying energy in a manner with at least the same degree of order. So to put it simply, to get order, you need order.